Good afternoon. We'll give people maybe another minute to settle down. Hope everyone had a good lunch, and for folks from overseas trying to stay awake in the afternoon. Before we start the session, actually, I'd like to remind you that there is a survey sheet in your book. We will appreciate you to fill out so that you can give some good appreciation to the speakers, and also if there's any suggested improvement, please feel free to put it down so we can always make the course better in the future. So the survey sheet is in the book. You can fill it out and hand it in before you leave at the end of the short course. Okay, so we have a full afternoon with 3 more lectures coming up. The first one is on the back-end manufacturing technology, followed by 300mm manufacturing, and then yield and reliability challenges for the deep submicron era. There will be a coffee break after the second lecture, after the 300mm manufacturing. So you do have to stay awake, hold on for 2.5 hours. Okay, so let me introduce Nobuyoshi Kobayashi-san. He's currently program manager of back-end processing of Solid in Japan, leading the 65 nanometer copper and low-K Asuka project team in Japan. He had 20 years of experience at Hitachi, working on the metallization, DRAM, tantalum oxide, and copper low-K, and so forth. So let's welcome Kobayashi-san.
Thank you, Jack, for introducing me. My name is Nobuyoshi Kobayashi from Solid, and I'll talk about back-end manufacturing technology today. I'll start by describing the trend in interconnect scaling. Then I'll talk about technology challenges for 65 nanometer back-end process. Then I'll describe new IRD materials that are needed to break through the lead bricks, so-called. And integration of these new IRD materials is very difficult and complicate the conventional process. I'll explain the detail of the integration challenges of these new materials. Then I'll describe the reliability problem. Finally, I'll summarize my talk. This picture shows the first fabricated IC by TI in 1958. It's somewhat difficult to see where the wiring is, but you can see this wiring between the devices in the first IC chip. And this picture corresponds to present day copper low-K interconnects. As you can see from these figures, there are drastic change in a device structure for these 50 years, like a half century. And the changes are occurred mainly in two areas. One is the scaling of interconnect has drastically shrunk. And the other is the number of interconnect layers has been drastically increased. I'll explain this change in more detail. This figure corresponds to a multi-level interconnect in logic LSI from 0.5 micron to 0.18 micron technological node. As you can see in this figure, along with the device scaling, new technologies have been introduced every technological nodes. There are many new technologies like this. If I can explain these new technologies in detail, maybe I can conclude my talk just in 6 minutes or so. But among these, the introduction of copper is the most drastic one. And now we are facing the new challenge for a 300 millimeter and 90 to 65 nanometer technological node, and special challenge is low-K introduction. Copper is drastic. Copper process is drastic is because the process of copper is completely different from aluminum one. Copper is formed so-called by using dual damascene method. In the damascene process, the interconnect pattern was initially formed in the oxide, and copper electroplating filling and copper CMP followed. Damascene process consists of single damascene and dual damascene process. And in the manufacturing, a dual damascene process has been widely used because the fewer process steps. This is ITRS roadmap of 2001. As for the scaling of interconnect, is indicated for each layer. This is local wiring, intermediate wiring, and a global wiring. And also, the scaling of barrier metal thickness is indicated like this to suppress the increase of copper resistivity. And as you can see, for the introduction of low-K, you can see the red bricks here. That is standing to develop a 65 nanometer technological node. This figure shows the interconnect parasitic capacitance with the interconnect pitch. In a 0.180 nanometer technological node, we use SiO2 ILD. In that case, K effective is 4.5. But in this case, with scaling interconnect pitch, parasitic capacitance interconnect is drastically increased beyond 90 nanometer technological node. That's why we introduced the low-K. For example, 130 nanometer technological node, the K effective 3.7. For 90 nanometer, we'll use the low-K with the K effective 3.1, and for 65, K effective 2.5. These values are almost constant with the roadmap values. To adopt these kind of low K, we can we can make the project capacitance almost a constant for every interconnect pitch. In addition to the parasitic capacitance calculation, we investigated the impact of low K introduction in the power consumption of chip. This table shows the parameters we use for the calculation. And note that the number of gates becomes almost a fivefold from 180 to 65 nanometer technological node. That will increase the interconnect length almost 5 times. This figure shows the capacitance of interconnect and transistor for each technological node. Power consumption of the chip is proportional to the sum of interconnect capacitance and transistor capacitance. This figure shows the range in capacitance when the K effective value ranged from 4.5 to 2.5. The value is normalized by that of 180 nanometer technological node. As you can see, in a 180 nanometer, the transistor capacitance of the transistor is dominant. Whereas in the 65 nanometer, the interconnect capacitance is dominant. That's why we are introducing this low K value, low K materials. And the introduction of low K with K effective 2.5 will decrease almost 30% of power consumption in the 65 nanometer. Also, low K introduction is very important, so-called to reduce our RC delay. This figure shows the clock frequency with the year, the change of clock frequency by year. Local clock frequency of MPU is increasing rapidly like this, but as for the global clock frequency, it's the increase of global clock frequency is slow as compared with the local clock frequency due to the RC delay expressed by these expressions. Along with the low K introduction, reverse scaling of global wiring is expected to meet the high-speed operation requirement. This figure represents interconnect pitch versus technological node. The interconnects are divided in 3 categories. One is block wiring and intermediate wiring connecting blocks and global wiring connecting module. As for the interconnect wiring, the scaling is the pitch of intermediate wiring scaled like this. However, the pitch of the global wiring is increased drastically beyond 65 nanometer technological node. This means also the number of interconnect layer will be much increased to meet the high-speed operation requirement. Next, I'll talk about technology challenges for 65 nanometer back-end process. This figure represents the three main technological challenges for scaling. One is the low K, that was I described earlier, for a high speed and low power dissipation. The other one is for high density integration. For interconnect pitch scaling, barrier metal thickness scaling, and also the dishing-free kappa CMP is very important to suppress the distribution of the interconnect resistance in the wafer. And as for the cost is a very important factor to metallization, and cost determines the process, and reliable and highly manufacturable process is required. As for 130 to 90 nanometer kappa low K, there are many fabrications for low K material, fluorine doped SiO2. In this case, the K value is 3.6, and also we'll find the silk. This is organic polymer, and also carbon doped SiO2 have been widely investigated for these applications. As for the barrier metals, PVD of tantalum-based metal have been widely used. This figure shows the 65 nanometer technological challenges. The first one is low K ILD, as I mentioned earlier, that diffusion barrier that is put on the insulator above ILD to reduce the effective K values. The selection of low K thin diffusion barrier is very important. And also the interconnect scaling, thin and conformal barrier metal is needed, and void-free electroplating technology should be developed to guarantee the reliability. As for the CMP, dishing-free process, and also to prevent the delamination or the damage of ILD, low downforce process will be needed. As for the dry etching, the precise control of etching profile and also damageless process to ILD is needed. In addition, the compatibility of lithography is very important. As for the beer formation, the reliability of stress migration and electron migration is very important. To improve this kind of reliability problem, the interface property like adhesion is very important. Next, I'll talk about the impact of the K value of diffusion barrier and on the K effective values. The first, you should note that nowadays the structure of ILD is much complicated, like this. You know that we put a diffusion barrier and also a capping layer above a low K film, and the K value of these film has strong effect to the K effective values. This figure corresponds to the interconnect structure for our calculations. The thickness of diffusion barrier fixed at 50 nanometer thick. In that case, this is the result of K effective against the K of diffusion barrier. And this green region corresponds to target specification of 65 nanometer technology. For example, you can see if we adopt K value of 2 for IRD and K value of 5 of diffusion barrier, we can reach a target of 65 nanometer technology. This is a similar result for the effect of K of capping layers. The effect and effect of barrier K value is very drastic, as shown this figure. We assume the interconnect structure like this. As for the dielectric, 180 SiO2, and in this case, the structure is nitride and SiO2. K value is 4.2, and 65 nanometer, low K value is 5.5, diffusion barrier and cap low K. We use this structure, and this is the result of the calculation. The vertical axis represents K effective divided dielectric constant of IRD. This means below a 90 nanometer technological node, the effect of the K value of diffusion barrier and the capping layer is very important because the big difference between normalized values. I'll summarize the target specification for 65 nanometer from these calculations. This is an example of target specification. Low K IFD ranged from, the K value ranged from 1.5 to 2.0. The diffusion barrier, the K value is less than 5. In this case, etching stopper is not used. And also the similar conditions for capping layer that will reduce the K effective value from 2.2 to 0.5. I'll move to the topics of the metallizations, the barrier metal. And this picture shows the various copper seed layer deposited on various barrier metals. There are titanium nitride, tantalum nitride, tantalum. And all the deposition was conducted by using PVD. As you can see, the agglomeration of copper seed layer in the side wall, and that will induce some void when electroplating process is conducted. Thus, the conformal and thin diffusion barrier is very important. And also, the selection of barrier metal is very important in terms of the reliability of via thermal stability. These are some pictures after annealing 400 to 450 degrees C for 30 minutes. These are the barrier structures. As for the copper nitride, there is some, you can see the void after thermal treatment, and also if we put the titanium between the copper, this is the glue layer. The things are improved. But you can see that basically if we use a tantalum-based metal, this kind of stability is much improved. And possible mechanism is adhesion between the copper and barrier metals. So the selection of barrier metal is very important, and also we should make much effort to develop a conformal and thin film formations. But when this metal is adopted to deposit it on a porous material, there is some serious problems. That is the penetration of PVD tantalum into pore in MSQ. In this case, we use this low K and the porous MSQ. You can see this unclear and shaded region in the porous MSQ. This shaded region, you can see the copper and tantalum. This indicates that these metals penetrate into a pore in these low K materials. So this is also a big concern to apply this metal on the porous materials. LD is a very promising candidate to make up conformal and thin film formations. In an LD process, gases are introduced like this by cycle by cycle. And the precursor gas is absorbed initially at the surface of the substrate, then followed by a surface reaction to form atomic layer of metal. In that case, the step coverage is perfect. But the problem is in this LD, it's somewhat difficult to find very suitable precursor, especially for tantalum. Of course, there is some report on tantalum CVD precursors, but it's perfect. It will give a perfect step coverage, but the resistivity is very high at this moment. This figure shows the step coverage of LD tantalum field at a deep trench. You can see this very thin line, a black line, along with structure. This is tantalum nitride film with a thickness of 1.9 nanometer. So anyway, this LD deposition of tantalum makes a perfect conformal deposition, and it's very good barrier properties. This table shows the comparison of barrier metal deposition method among PVD and CVD and ALD. For PVD, the high quality film and good adhesion are conventional. There are advantages. But for CVD, it's very advantageous for good conformality of barrier metals. However, generally it has the poor adhesion, and also the impurity incorporation in the film is a big problem. This is a summary of this session. I've described the low K integration, the impact of diffusion barrier, and target specification. As for all the interconnect, copper dual damascene interconnect, barrier metal has a very important role. And also, the interconnect scaling requires CVD metal seed and barrier metal, but metal penetration is an issue. LD is a candidate for conformal deposition. No clear decision of CVD material at this moment. Next, I'll describe new ILD materials. This table shows the typical low K materials for copper integration. Sorry, maybe you can miss these figures. I add this figure later. And low K materials can be divided in non-organic and organic dielectrics. And to reduce the value of K, there are two approaches. One is to reduce the polarization of component molecules. SiOF, fluorine-doped SiO2 is an example. Fluorine doping reduces the electronic polarization of ILD. The second approach is to reduce the density. That may be, we use porous materials. They include porous silica, porous SiOC, porous MSQ, and also there are non-porous materials like polyethylene-based or Teflon-based materials like this. For a 65 nanometer technological node application, we select several kinds of porous material and non-porous material. This table shows structure and materials direct constant deposition method. At this moment, there are many MSQ because the development of porous MSQ is mainly done in SOD film at this moment because the formation of pore is somewhat, established in SOD case, but it's somewhat difficult how to make a pore in a CVD film. So these photographs correspond to the cross-section of these porous materials. This figure represents how the development of copper-Low-K integration will proceed. The first, Low-K characterization will be done to select the materials. Then, to check the feasibility of material, the module integration will be done. Finally, I'll evaluate reliability. There are many feedbacks between the steps. Next, I'll talk about the Low-K characterization. This table shows there are typical evaluation items and methods. There are, for example, the direct constant, Young Modulus, hardness, structure, and pore size, and so on. These items were evaluated by using these analytical methods. First, I describe of the Young Modulus. Young Modulus is the parameter of mechanical strength of Low-K film. This figure shows the modulus as a function of dielectric constant K. As you can see, this figure, the Low-K film, especially for porous Low-K film with the K value less than 2.5, the modulus is about 1/10 compared with the reference Chaos SiO2 film. So in that case, the poor Low-K material is very, very weak in the mechanical strength as compared with SiO2. Note that this point, this is non-porous material of organic polymer, like polyethylene-based polymer CVD. In that case, the mechanical strength is as high, above 10 gigapascal. And also, there is some correlation between the modulus and pore size. The pore size was evaluated by using a small angle X-ray scattering method. This is a figure of the correlation between the modulus and average pore size. There are big scatters among these materials, MSQ, HSQ, organic polymer. However, there is some strong correlation if the material is restricted in an MSQ, porous MSQ, like this. So, small pore size and tight distribution makes the pore MSQ stronger. So that's very important to control this kind of pore size or distribution in developing Low-K materials. And also, there is some correlation between the direct constant and also modulus with the density of the film. In this case, all the samples are MSQ. MSQ is as indicated in the table. This is some carbon-doped SiO2 that is formed by SOD. There is a good relation between the direct constant density and also modulus, like this. The leakage current of low K material also is a big concern. This figure represents the leakage current against the reciprocal temperature. The leakage current is almost a similar level with the conventional TEOS in the porous low K in that case, but it has activation time type temperature dependence. The mechanism is not unclear yet, but it will maybe low K porous material has some trapping center for current. And also, this is thermal conductivity of low K film as a function of direct constant. The sample is ranged from TEOS and also organic polymer. As you can see in this figure, the thermal conductivity of porous low K is about 1/5 of the conventional TEOS. The thermal conductivity is also very poor. And also, we investigated damage and resistance of porous low K against the wet chemicals. This wet chemical is used to remove so-called residual polymer after dry etching. We try to 3 kinds of wet chemicals. There are fluorinate ammonia chemistry-based and chemicals, and the other is amine and acid. And we check the damage after dipping chemicals by changing the K value, and also we check the structure by FTIR and the change of the thickness. This is some result. We use various kind of porous MSQ films. In general, pH of the wet chemical is very important factor to discuss the damage for porous low K. And in these results, the K value is least in acid wet chemicals. So we should also develop this kind of suitable chemicals for porous low K integration. And also, we try to supercritical fluid application to porous low K. Supercritical state is occurred at a certain temperature and pressures. Their feature is high density than gas, a low viscosity. That will cause high supercritical fluid penetrate into small holes and react medium to enhance the chemical reactions. We adapted CO2 supercritical fluid cleaning to a porous low K. We adapted supercritical fluid cleaning after pre-baking at 250 degrees C. And pure annealing was followed by 35 degrees C. As you can see, the Young Modulus was almost twice after supercritical fluid cleaning, and this is because the supercritical fluid cleaning can chemically remove the template in the low-K film, and that will cause a smaller pore size. I'll summarize this session briefly. Low-K, I'll talk about the low-K candidate, porous and non-porous materials. And porous low-K materials, there are several concerns for integration. One is the first porous MSQ has been extensively developed at this moment. And the poor mechanical strength and thermal conductivity is a big concern. To improve this kind of material property, there are two approaches. One is material development, aiming at a small pore size and their tight distribution. The other one is post-process development. As I mentioned, supercritical fluid cleaning, and also in the literature, EV cure method has been reported. And also wet chemical with little damage to low-K film is important. Next, I'll move to our integration challenges. This picture shows possible CMP failures of copper low-K interconnect. There are metal delamination or cracks during CMP with a mechanical friction. To prevent this kind of delamination of the crack in the film, we should improve we should develop a new slurry and also a new pad, and also reduce the downforce process is important. This data shows the correlation between the Young Modulus and CMP failures. And this failure is strongly dependent on the sample structures, say pattern and blanket. For example, the Young Modulus is below 4 gigapascal. Pattern wafer, the test of the pattern wafer is okay, but not for a blanket. So there is some correlation between the mechanical strength and CMP failures. And this figure represents CMP downforce vs delamination area of capping layer. The sample structure is like this. We did this CMP experiment by changing the downforce from 3.5 to 1.5 psi. With reducing downforces, you can see the area of delamination is much reduced. And also note that delamination, the starting point of delamination is at the wafer edge. So to reduce this kind of defect, we should take care of some treatment of surrounding a wafer edge treatment, and also this kind of process improvement. And etching damage is also very big concern for low-K integration. This figure shows porous MSQ, the plasma treatment, FTIR spectra after plasma treatment, the sample is porous MSQ. Acid gas is ammonia. In that case, we change the pressure of ammonia. As you can see in this figure, after etching, the K value is increased much, like 2.2 or 2.5. Simultaneously, we can see a water desorption in the film, and the chemical bond CH3 was broken. This is some damage of etching. So we are investigating several kinds of etching gas against the porous MSQ and porous organic polymers. if we use oxygen, the thing is it's very bad, much increase in the K value, and also, in the case also organic polymer. If we change the acid gas into ammonia and nitrogen and hydrogen, the situation is much improved, but still some increase in K values for porous MSQ. Thus, we should improve this kind of etching technology more to reduce this kind of K value change. The work will be this kind of work has been done recently. As for the damage of low K material, the lithography is closely related with kind of to prevent the damage of dry etching. We use a dual hard mask etch. This is two mask layers put on porous MSQ. The first mask was patterned by using a conventional photoresist. Then resist was moved in this state. The point is the low K was protected by this capping layer from etching damage. So this, by using this first hard mask etching, we etched low K material. But it is somewhat promising to prevent etching damage. However, also this process is very complicated, and it will increase the cost of the process. So it is somewhat trade-off. So along with this kind of approach, still the conventional single resist process should be investigated. Recently, there is some the integration of porous low K MSQ. K value is 2.2 has been demonstrated in the last BLSI symposium. In that case, SOD film K value of 2.2, and this kind of 6-level copper interconnect has been demonstrated. And it is the breakdown electrical field between coppers are almost similar with the conventional process. So there are many problems with porous materials, but this kind of integration work has recently much progressed. As for the integration of front-end process, negative bias temperature instability of pMOS is a big concern. As for this figure shows, this is the VTH shift with the stress time. The sample was compared between a wet oxidation gate oxide and dry oxidation oxide. In a wet process, the VTH shift due to a negative bias temperature stress was much increased. The mechanism of this kind of increase is not clear at this moment, but people believe some hydrogen forms some interface state with a combination at the interface of gate oxide. And this will make some fixed oxide charge in SiO2. If we adopted porous low K into their devices, the poor water absorption is a very big concern. And if the hydrogen in the film is, diffused into a device or something, there is a concern to make this kind of negative bias temperature instability. This is the future work. And also, if we adopted porous low K, packaging is very important topics. Concerns are mechanical failure by gold and aluminum bonding and also thermal stress. And how about the compatibility with emerging packaging technology like BGA, CSP, flip chip, or CIP. This reports the package failures after gold ball bonding. They are checked. This is the semantic data. They are investigating gold ball bond, aluminum wedge bond, flip chip bonding. This is the site of packaging failure. It's the same place. As you can see, there is some delamination between a copper and MSQ like this. And in that paper, they said additional layer solve the lamination of aluminum pad or porous low K. They are thick passivation onto low K film. In that case, the other is also a copper SiO2 dual damascene structure onto a copper low K process. By adopting these two approaches, the packaging failure was much improved. I'll summarize this section. Integration challenge. I'll discuss about CMP compatibility and low down CMP with a highlight. And also, damage-free etch is very important. I'm discussing about the plasma chemistry of etching and also high selectivity etch. As for the lithography, dual hard mask and resist mask, the trade-off program I discussed. And the important thing is also the resist poisoning problem. As you know, there are ARF lithography. There is some big resist poisoning problem, but we are not sure about the next generation lithography, F2 or other electron beam. This is also very important topics. As for the front-end process, NBTI reliability I've discussed. In addition, this kind of reliability, if we adopted high K integration, high K is very sensitive to hydrogen. Also, this is very big topics to be investigated. As for the packaging, we discussed just for a BGA or a flip chip. These kind of investigations are now undergone. Then I'll move to a reliability problem. Reliability is the final step for module integration, but they are very critical for interconnect scaling. The reliability problem is electron migration reliability, bare stress migration reliability, TDB, package compatibility, as I mentioned earlier. First, I'll discuss about electron migration reliability briefly. This is median lifetime of electron migration against the inverse of the temperature. This is some width by height of interconnect. All the points correspond to a copper interconnect except this line. This is aluminum. As you can see, this figure, the activation of electron migration lifetime is almost similar among aluminum and copper. The activation energy is 1 eV. And if the interconnect area is small, the electron migration lifetime decreases like this. But note that damascene copper line is much bigger than the aluminum line. That's why we adopted a copper interconnect at this moment. And also, this figure plot the ratio of the median electron migration lifetime divided the lifetime of the wide, the area, the interconnect area is 1.3 by 1.9 micrometer squares. As you can see, if we plot this kind of lifetime ratio as a function of interconnect area, it's interesting, it is proportional like this. This means lifetime drops as dimensions are scaled down. And also, this lifetime is proportional to the area of this copper interconnect. That indicates this mechanism of this failure is the interface copper diffusion. So the problem is the required chip current density scale up while the electromagnetic lifetime is decreases with scaling. This is some big issues. To improve electromigration, some capping coat on the copper is effective because if we put some capping layer onto a copper interconnect, that will prevent the copper diffusion at the boundary surface boundaries. So in that case, copper, tungsten, phosphorus film was deposited by electroselective deposition technique. And these pictures correspond to the failure mode. This case is no metal cap, and this is a cobalt cap samples. So this kind of improvement of a copper interconnect and also the impurity addition is effective to improve electron migration reliability. Next, I'll talk about stress migration voiding reliability problems. This figure shows a failure of the beer chain's failure rate against the width of interconnect. As you can see, if the width, the line width is bigger than 3 micron, the failure rate was much increased, like this. And also, it has a dependence of via diameter. And you can see in this failure, you can see a void at the bottom of copper interconnect. And very interesting thing is that this kind of failure has a strong temperature dependence. The failure rate has a maximum at around 150 degrees C. To explain this kind of voiding failure, they measure the stress of copper lying on beers by using the X-ray diffraction. This is some result of stress and width, and also the stress as a function of diameter. The stress is divided in a Z component and X and Y component. And as you can see in this figure, there is very unique dependence of stress as a function of width and also as a diameter. Stress migration formation is related with the Z component of sigma of beer minus Z component of line. So in that case, you can see these experimental results can explain why the in the wide lines SM void failure has has occurred. And also there are another mode of stress migration. In that case, the void was formed at the upper side of the interconnect. So like this. And also this kind of stress migration voiding in beers has strongly dependent on temperature, like this. They are maximum at around 150 or 200 degrees C. They think this stress migration reliability is caused by the stress distribution of the metal like this. The first, this is the electroplating copper film. After some heat treatment, the grain growth is proceeding like this, but there are many defects like this. In the thermal treatment, these defects accumulated at an interface between bare and line will make some void in lines. So there are this kind. I spent some time to explain this kind of stress migration program because this reliability is very, very serious at this moment in the manufacturing point of view. So in this IDM, there are lots of papers. And also there are several kinds of mode. But the only thing we can understand is, anyway, this is related with stress and the temperature. The other one is I'll explain the TDDB reliability of ILD. Also, this is very serious for interconnect scaling. The first copper was, the fast copper diffusion used bias temperature stress was reported in 1985. To prevent this kind of fast copper diffusion, we put good barrier around the copper, like, the tantalum nitride and capping SiO2. But thing is not completely solved by this kind of cap, by using cap layer and barrier metal. Because at this moment, the breakdown point is not between the line, but the interface between a copper and lines, interface between a copper capping layer and ILD. For example, this TDDB lifetime is strongly dependent on process condition like this. For example, this is a process of copper interconnect, copper deposition, followed by a copper CMP. Then we'll conventionally do some plasma treatment to make a good adhesion between a capping layer and ILD. We use typically use an ammonia plasma treatment. This removed some contamination on ILD and also to reduce the copper oxide surface. This kind of ammonia plasma treatment has a strong effect to a TDDB lifetime breakdown like this. This figure shows the time to failure of TDDB as a function of field strength. This is 10 years. We should guarantee these criteria. As I mentioned, we did a pre-treatment by using ammonia plasma like this. But know that the lifetime was, the almost five times in order of magnitude has been improved by this kind of plasma treatment. This result implies TDDB is governed by the interfacial diffusion of copper, not for the bulk copper diffusion. So it's very important to improve this kind of interfacial properties with the copper interconnect scaling. I'll summarize in the reliability section. Interconnect reliability, this is key to successful copper-low-K integration. EM reliability is, the lifetime decreases with scaling. As for the BRSM reliability, copper interface diffusion caused by ILD stress change after thermal cycling is an origin for this reliability issue. Therefore, the adhesion of ILD and barrier metal and copper interface is very important. As for the TDDB reliability, plasma treatment is very effective. Finally, this shows the trend of K effective for in the ITRS roadmap. As you can see, in these 3 years, the introduction of low K is much delayed, like this. In the 99, this blue line. At this moment, the latest version is like this. So the background of this delay of low K introduction is mainly due to some reliability problem associated with the copper scaling. In that sense, a copper process is very effective to improve the device performance, but it is not mature at a manufacturing point of view. So if we introduce a porous low K into the copper low K process, the much work and also the physics and the mechanism of this kind of failure is indispensable to make this kind of copper low K technology into manufacturing process. But the great progress has been made recently. Maybe as you can see this progress in this idea. I'll summarize my talk. Low K is very important in high speed and low power dissipation. The porous materials will be inevitably introduced to reduce 65 nanometer. They have fundamental issues to be solved. Along with interconnect scaling, the liberal scaling also will push the technology to be combined with the packaging. Reliability issues with new ILDK have been great delayed low K ITRS roadmap, but final decision for low K depends on cost. So clever solution is very important to introduce a low K materials in productions. Thank you very much for